I'm going to explain an algorithm that does that applies optimal transport to color transfer, no? To transfer color from one image to the other. So in our context, we're going to be talking about discrete distributions. So we have mu0, that is our original distribution, and we want to map it onto mu1. Both, well, they are both histograms, and they both have the same mass. There are two things that are important for us. On one hand, the optimal transport cost. So how much does it cost to take this mass, this distribution, mu0, onto mu1, and the optimal transport map. What is the map? How do we have to take mu0 onto mu1 to obtain this optimal cost? Optimal transport has been applied in image processing to a lot of times, as in general in the context of statistical-based tools. For example, to compare for image retrieval, not to see which image is better in a database. That would be the cost. Also for object segmentation. On the other hand, the optimal transport map has also been used for texture synthesis, for constructing different textures, different types of textures, or for color transfer before also, or for shape matching. So in our context, what we are interested, this is our problem. In our problem, we have an image, an original image, that was this one here, and we want to take the histogram of another image. The histogram, so this discrete distribution. So what we do is we're going to map the histogram of this image onto this one to obtain this one here. In general, just the optimal transport has two limitations, because as we said before, the histograms had to have the same mass. In our context, this means that the images have to have the same size, which is completely unrealistic. And another issue that we're going to have is that this transportation map may be fantastic to take one distribution to another, but in the color space it's not going to be regular. So this is going to introduce a lot of artifacts that we might not want. Okay, so we're going to deal with these two issues. I will start by explaining how do we compute optimal transport between histograms. I think you have heard a little bit about this. And how do we modify it to apply it to color transfer, introducing a relaxation and a regularization term. Okay, so in our case, what we have is two distributions or two sets of points x and y, each point in dimension d, and we're going to have n elements. We're going to assume that our distribution, in our discrete distribution, every point has equal mass, 1 over n. So then we have the Wasserstein distance going to be this distance here. So for every element in the first data set, we want to find the best matching element in the data set y, and that's going to give us the overall cost. So what does it mean to find the best element on the other data set? It means to find the permutation matrix that maps x onto y. So let's see. Imagine that we have, this is our discrete distribution x, this is our discrete distribution y, and this is going to be our sigma. For every element, we want to find a mapping on the other distribution, on the other group of points. Of course, this is very well known. This is the optimal assignment problem. Yep. And and it can be very easily solved when d is equal to 1, when our dimensions are 1. Okay. What happens if we start modifying this context? What if instead of having a set of distributions with equal mass, now we want different masses for every point? So now we need to redefine our distributions in a slightly different manner. We're going to define our distribution mu of x composed by deltas located at a certain point x of I and with a mass mi. Okay? So since we want this to be a distribution, the overall sum of the masses has to be equal to 1, and all the masses have to be bigger than 0. Okay, in this case, In this case, we know how to compute the optimal transport, and it involves computing the inverse of the cumulated histogram on both distributions. Let me show you an example. Let's say that we have this distribution here that is mu 0, and this distribution here that is mu 1. And we want to compute the transformation from one to the other. In this case, what we need to do is, this is basically an exemplification of the formula that I just showed you. First, we compute the accumulated histogram of both. We compute the inverse, and we do the transfer there. We find, let's say, for example, the midpoint histogram, and we undo what we just did, obtaining the final distribution grid, right? The midpoint density. Okay. So we know how to do this for distributions that are in dimension 1. This is easy, we know how to do it. The problem is that when our dimension is higher than 1, when our points are in dimension bigger than 1, we cannot invert the cumulated histogram. It doesn't exist. So we need to see what we can do. Okay, so in this context, when our dimensions are bigger than 1, we can recast the optimal transport calculation as a linear program. In our case, let's go through it a little bit. Here, we still have the same distributions, but now our points are going to be in a higher dimension. So what we need to do is, we're going to recast the optimal transport as a linear programming problem, where we have linear costs and linear constraints. So this is our problem. The overall cost is going to be, we want to find the P matrix, there's a probability matrix, that minimizes this expression here, where this is the matrix cost. So the cost between the point x1, xi, and yj is going to be defined like this. Okay? So we find the distance between the points, and the P is going to be the probability matrix. What does that mean? This means that every element has to be bigger than 0, the sum of the overall mass has to be bigger than 1, and the marginals, and this has to be the marginals of mu and nu. So just, okay. It doesn't pass. Okay, now, yeah, okay. So just a little example in dimension 1, of course, this would be in bigger dimension. Let's say that we have two histograms, the violet one and the blue one. These are the locations of our points. This would be x3 with mass 1/3. This would be mu2 and sit in the position 7 with mass 2/3, and so on for the other one. The matrix, the cost matrix would be the difference between the positions. So in the 1, 1 is going to be 3 minus 1 squared, so that's why we have 2, okay? And P is going to be the possible matrices, where every position that links mu1 to nu1 is expressing how the mass is transported from one point to the other, okay? So for example, well, this could be, and the overall cost is going to be just the sum. This would be the cost for this given function, for this solution, and the optimal is this one here. Okay, so imagine that we have two distributions that are this one here, that is mu and nu, where this one has only one cluster and the other one has two. It's very important in this case that we allow splitting of the mass. So in this case, well, exactly, using this P matrix, what we can do is we can match one of these bins to a group of other bins. Okay. So this can be solved. We know how to solve this. There's an algorithm that has been solved before. It's a standard linear programming problem. The thing is that we have algorithms like the simplex and interior points methods that are pretty good, that get good results for situations where we have thousands of points. But in image processing, that means that we can only process an image that is 100 by 100, or something like this. So this is not realistic. We need more stronger algorithms or faster algorithms. On the other hand, the good thing about these algorithms is that the complexity does not depend on the feature. So we can, on the dimension of the feature. Of course, there are algorithms that are specific for these cases. That is, like, for example, the Hungarian, but it's basically the same situation. We still need, they're not fast enough. Okay, so let's go to the part of where we can apply this to our case. So, as I said in the beginning, using optimal transport directly to transform the histogram of one image into another can have, has strong limitations. First, we're going to generate a lot of color artifacts because the map is not regular. So we're going to introduce, it's not regular. And also, and this is what happens here. Here we have an image where we change its intensity, and suddenly all the noise that here was all this area that was very similar becomes super noisy and with a lot of artifacts. This is because in the regularization we have separated colors of pixels that were very close here. And here, there's a filtering that you do afterwards. So this more or less shows that introducing regularization can improve the results. Of course, as I said before, we are also going to need a relaxation of the mass conservation constraint, because we want to be dealing with different histograms and so on. So, first idea, relaxation. So this is the definition that we had before. No, we want to find the P matrix that minimizes this expression, and these were our constraints. These two are related to the fact that P has to be a probability, and these are related to the original histogram and the final histogram. So what we're saying is that, okay, we want to relax the constraints on the mass, on the final mass. So we're going to allow, instead of matching to nj, we're going to allow an interval. Yeah, from kng to big kng. The problem is that to tune these parameters is very difficult. So what we're going to do is we're going to introduce this kappa constraint in our energy. We can see that we still have a linear program. This is linear, and the constraints are linear. Okay, so what does it mean? Let's say that we have these two sets of points. This will be our x, this is our y. As you can see, we have two clusters, and this line means that this point is going to be assigned to this point here. Okay, this is what I was saying, that is not regular, the mapping. We would prefer to have a mapping that is more regular. That is exactly what we get here. The relaxation allows to map these points to these points here and to lose points here. Okay. Okay, so let's see what is the result just using the relaxation on the optimal transport. This is our original image, and we want to put this histogram onto this image. If we just use optimal transport, we see that the colors are getting outside. We're not maintaining the clustering that we have here in the color space. The colors are getting outside of the white region. If we introduce the relaxation, we see that, we can maintain the pixels that are close together. Okay, let's add now the regularization term, which is just going to be a term in the overall energy. We know that computing a regularization on this matrix is going to be NP hard. So instead, what we propose is to compare for every x, we're going to compare it with an average of y. So let's say that we have this x here. Instead of comparing it with what would be our y's, we're going to compare it with this average value, which gives us a vector field v. Then what we're going to do is we're going to create in the color space, in the colors spatial space, we're going to create a nearest neighbor graph. So we can impose regularity on this space. And over this, we're going to compute, we're going to define the graph Laplacian term, that's this one here. So the final penalization is this one here. To compute the NNN graph, we're going to introduce a little bit of spatial information also. So let's see an example. We have, again, the two sets of points. We computed the graph, the nearest neighbor graph. And now we want to compute the transport. So this will be the relaxation, no, that we're mapping these points here. And now there's a change with the regularization. So we can see that, well, it's more regular. Okay, so the final process is the following. We first compute what is called in image processing superpixels. There are some kind of segmentation, small segmentation that you can see here. For example, here you can see a lot of details, and here you see areas that are kind of flat. So you have areas that are defined by color and space. They are proximity in color and space. This is going to give us a simplification of the image that we're going to use after to do the clustering. Okay. Over the superpixels on this version that is reduced, we're going to compute our optimal transport map, and then we're going to apply it to the final image. Okay, so these are some examples. We have this image here of a parrot, I suppose, and this we want to impose these colors on this image. So this is the result that we obtain, and well, these are others from the state of the art. For example, we can see that yeah, we're avoiding some artifacts and so on. Some other examples, we have this image here. We want to impose the colors of this image, and we get this image here. Same example. Well, same example, no. Different example, same location. Okay, well, I think you got the idea. So, to conclude, the relaxation is well, in image processing problems, it's necessary to make it reasonable, let's say. Spatial regularization is also important to deal with artifacts. It's true that is still very expensive, computationally expensive to develop this kind of algorithms. And it could be improved maybe introducing some kind of semi-automatic methods. Yeah. And this is basically what we were thinking for the future work. Faster implementation using some other kind of statistics, not using only color, but maybe some other kind of features and other kinds of regularization. So this is it. Thank you very much for your attention.
Thank you.